Now, for most of us, we can type in log base 2 of 6 into our calculator because our calculators have that technology. Some of us have calculators that don't have that technology to write the little 2, and you can write it as log 6 divided by log 2. So one of the things that we're going to find is we're going to say, well, let log 2 of 6 equal x, right? And if we do that, we could change the log form to exponential form. 2 to the x equals 6. Now, log is a function, so just like any other function and just like with any other equation, would you agree that if 2 to the x equals 6, that log of 2 to the x should equal log of 6? Does that make logical sense? Just like if you square both sides, they're still equal. If you have one side equal to the other side, and you take the sine of that side and the sine of the other side, they'd still be equal. As long as it fits within the domain of the function, that should make sense. Now, at this point, you have a log law. If you have a power inside of a log, what can you do with it? You can bring it outside. So I could write this side as x log 2, and it would still equal log 6. How could I get x by itself? Log of 2 is a number. You could divide both sides by log of 2. And what did x originally equal? We originally said x was equal to log base 2 of 6, and we've just proven that then x is also equal to log of 6 over log of 2. And this is going to form the idea for the last formula up on the wall, our change of base theorem. I'm going to do it again. But this time I'm going to choose a different base. Which bases are on every calculator? Which buttons do you have on your calculator? You have a log button? What's right underneath the log button? The natural log button. So instead of taking the log of both sides, I could have taken the natural log of both sides. Natural log is the same as a log. A log has a base of 10. Natural log is a log with a base of e. But all the same log laws apply. What happens when you have an exponent inside of a log? It can come out in front. Natural log of 2 is a number. How do I get it by itself? How do I get x by itself? I'd have to divide by natural log of 2. So this is equal to these. They're all the same. Can you see that if I wanted to, I could have done this again with another base? Instead of taking log with base 10 of both sides, I could have picked log of base, let's try to choose an underrepresented number. When was the last time you saw 731 in a math question? Yeah. Can you remember? Just the other day? Oh, shoot. Should we pick a different number? Okay. All right. That's maybe what? 8? 32. And so then these would all be 32s in here. And the answer would come out the same. So this leads to something called the change of base theorem, which is explained here and is highlighted on your next page. That if you want, you can take any base, log base b of x, and change it to any other log base. So I'll write it out here. Log base b of x equals log a of x over log a of b. The key to this formula is to notice that the letter a only appears on the right-hand side. So I'm going to highlight it right now in yellow. Here's the letter A. It only appears on the right-hand side. Whereas the letter B, whoa, there we go, there's B. The letter B is on both sides, and the variable x is on both sides. So color coding it this way, I can say log 3 of 7 is equal to, and I can choose 10, but I could choose 32, there we go, represent that number as much as you can. I could put 32 there. If I didn't want to put 32 there, I could put E. Well, they're the base of the log, so they're not actually a number. We can't cancel it out. Oh, let's put 17 in there. You could choose anything you want on that side. It doesn't matter. That A is just something you want to use. So normally, we choose it to a log base 10 because that's something we can type into our calculator, right? But if you wanted to type in, 785, you could put in 785 as a log base. I don't know why you'd want to do that, because it would be a lot quicker just to type in log base 3 of 7. Okay? But before calculators had the ability to type in different bases, they often only had log and natural log. And so you would change everything to logs and natural logs to be able to figure it out better. So in these ones it says approximate each logarithm to the nearest thousandth. Well, you'd have to use your calculator for this. And so sometimes if you forget where the change of base is, or where to type in the little 5 for log 5 of 50, you might want to write this one as log 50 over 5 and type that into your calculator. Or you might want to type in natural log of 50 over natural log of 5. So we're going to quickly look at that on our calculator just to see that those are all the same. So first of all, if you remember where the log base is on your calculator, you can type in log base 5 of 50, 2.43. But you can also write log of 50 divided by log of 5. Notice they come out to the same answer. Or you can choose the natural log of 50 divided by the natural log of 5. And what number did I say was, if you really wanted to, right, you could go 32. That's our underrepresented number for the day. So you could go log base 32 of 50. And again, we don't know why we would want to type in all of these extra numbers. Log base 32 of 5. They all come out to the same answer. Now, the reason the change of base theorem is nice is your log laws only work if all of your bases are the same. So sometimes if you have two logs in different bases, then you would want to change them to be all the same base so you can still apply your log laws. So for example, second example, log 8 of 6. Again, you could just type that in directly if you have that ability. Log 8 of 6. But you could just also do log 8 divided by log 6. And for me, that's actually, log 6 divided by log 8. Ooh, log 6 divided by log 8. There we go. To get the same answer. 0.861. We never did write the other one down to the nearest thousand. 2.430. Well, rounding, is it 43431? Okay, so questions for practice on this one are 3, 4, and 5.